Welcome, this is Xianghui. We present visibility-aware human object interaction checking from single RGB camera. In this project, we want to check the human, object, and realistic context between them in 3D from a monocular RGB camera. The object needs to be checked accurately even under heavy occlusions. Prior state-of-the-art CHOR suffers from two limitations. First, their human is predicted at fixed depths to the camera, and the object is not robust under occlusions, leading to inconsistent checking. To address these problems, we propose to condition our prediction on simple meshes with constant shape and leverage nearby frames to recover the occluded object. With our careful design, our method significantly improves over the prior art CHOR and can consistently and robustly check the human and object even under heavy occlusions. Next, we present our work in more details as outlined here. Modeling human object interaction allows lots of applications such as realistic motion synthesis, robot navigation, and scene understanding. However, existing motion capture system is very expensive. Here, the Wacom system requires optical marker and 54 cameras, which is expensive and not scalable. On the other hand, mobile phone cameras are ubiquitous and can capture high-quality images. It is highly desirable to have a method that can capture interaction from RGB cameras early. Nevertheless, 3D reconstruction from monocular RGB is very challenging. First, 3D reconstruction from monocular RGB suffers from depth scale ambiguity. Secondly, during interaction, objects can be heavily occluded, which makes the inference very hard. Recent work CHOR proposed a method to predict 3D interaction field from input images. As mentioned earlier, they suffer from inconsistent translation, and it is not robust to occlusions. We present two key ideas in our method. First, by using same simple shape as reference for scale, we can obtain meshes with consistent translation, which we call SMPL-T. Conditioned on it, we can check the human with consistent relative translation. Second, predicting from single frame is hard when the object is occluded. However, if we know how the human and object move in nearby frames, we can reason the object given its visibility information. Hence, our second key insight is to leverage the information from neighboring frames to predict the occluded object. Based on these ideas, we built our method as shown here. First, we estimate the simple T meshes that have consistent relative translation across the video. We then encode the simple T meshes using triplane to provide distinct features for each query point. This improves overall prediction but still does not handle the occlusion problem. We then use human and object visibility-aware network to predict the object pose under occlusions. And finally, we jointly optimize both human and object. Let's look into more details about the simple T conditioning part. From input RGB sequence, we fit a simple model with constant shape into the video. This ensures the constant body size over time and hence temporally consistent distance from the camera, which we call simple T mesh. We then render the simple T mesh from right, back, and the top-down views. The rendering is encoded with triplane representation together with the input image feature. And then we use a simple T conditioned network to predict a simple T conditioned interaction field, which consists of human and object distance field, simple path correspondence field, object pose, and visibility field. The object visibility field is used later to predict the occluded object. To handle occlusion, we introduce visibility-aware object pose prediction network. Given the human and object motion from all frames, we mask out the occluded object using the visibility prediction from SafeNet. And then we use transformers to encode human and object features together to predict the object pose. This prediction helps us recover the occluded object. With our careful design, our method obtains more consistent relative translation and is more robust under heavy occlusions compared to Chor. We show more results from our method. From this table, we can see that our method outperforms all existing methods in all evaluation metrics. The improvement is more than 50% when we evaluate using the matrix that is more relevant to the video. Now we show video checking results. We first show results on behaved dataset. We can see that Chor gives some reasonable results when object is mostly visible, but its performance drops significantly when the object is occluded. Our method, on the other hand, leverages the human and object visibility information, hence can robustly check human, object, and the context between them, even under heavy occlusions. We show another example from behaved dataset. We can see Chor is unstable and fails under occlusions. Our method accurately checks the human and object in the full sequence. Next, we show results from the intercap dataset. We can see the chair pose is not predicted correctly by Chor when it is occluded, and the 3D contact reconstruction is not coherent. Our method checks the seating interaction more accurately. Our method generalizes well to another dataset without network fine-tuning. It can be seen that Chor is not stable and does not capture the realistic contact between the human and the backpack. Our method is more coherent along the full sequence. We show more results from our method on NTU RGB dataset. We discuss limitation and future works in here. One future direction is to improve the object pose prediction when it changes significantly between two visible frames. Second, our method struggles to predict correct pose for symmetric objects. Future work can further reason the object symmetry explicitly. Thank you for watching. Our code and models are publicly released.